Okay, that's October 23, 2023. And we are done with chapter 4. Okay, 4.1, 4.2, 4.3. 4.2 has two parts. First law of motion of Newton has the first part is for masses at rest. The second part for masses moving with constant velocity, an object moving with constant velocity. The ancients understood pretty well the first part of the first law, but they didn't quite understand the second part because they also did not understand the forces of friction, how forces of friction behave. Then we went into the second law of motion, vector nature of Newton's second law. Newton's third law of motion, I covered that as well. And types of forces. Let's see here. I want to. It's wrong here. Let's see here. Newton's third law. Let's see what's the prime. Okay, yeah, this one you don't have to worry. The 4.6 you don't have to worry because they talk about, well, you have to worry about the gravitational force, right? But the strong nuclear force and metric forces you don't have to worry. Okay, so let's include that right here. Yeah, in a way you have to know about a little bit about this chapter, but you can see that it's very short as well. That's 4.6, and for some reason my notes here started 4.13. You shouldn't do that. I think I can fix it. And must be here. Yeah, okay. We start at 1. Nah, I hate that. Set numbering value. Go. That's not what I want. I want 4.1 here. You know what? I'm just gonna put the section number here. Yeah, okay. So now we have it. Now don't skip this one, you know. Chapter 4, section 1, 2, 3, 4. So we are types of forces. Types of forces. Types of non-contact forces, right? The book didn't say that, but it's type of non-contact force. So we have covered everything here, the gravity, and then it goes into the gravitational force. That's important for you when we start working on the electric force in physics 7. Normal force, I told you at the very beginning, static and kinetic force, the potential force. And then 11 and 12 are just examples of how to apply Newton's law, okay? I want you to look at examples there. And so you can become familiar how to solve problems with Newton's laws of motion. And what we are going to do now is to start uniform circular motion. Chapter 5. And let's see, the exam, when is the exam? We are writing here 23rd. The exam is going to be Wednesday next week, 1 week and a half, okay? And then I'll tell you what would be the chapters that we're going to cover. Definitely chapters 3 through 4. I'm not sure if we're going to have time to cover chapter 6. Okay, if you finish chapter 5 today or next Wednesday, I will add chapter 5 here. And exam chapter 3 to 4 so far. And don't forget, we're also going to cover lab 2 as well. Lab 2. Material for the second exam. Let's take a look at uniform circular motion. Right? I will say this one. Going back to these notes right here, chapter 5. We will start chapter 5. And material for the second exam so far. I'm gonna put here lab 2, right? Chapter 5. Uniform circular motion. Okay, so this is circular motion at constant speed, not constant velocity. Not constant velocity because the direction of the vector velocity changes, even though the magnitude of this vector does not, okay? That's why it's uniform. It's uniform because of constant speed. It's circular motion because it undergoes a circular motion. Okay, so let me show you an illustration of a circular motion. Let's see this one here, if it's a good one. I like this one that have better illustrations. Took me some time to find it. Okay, and 1D motion. Circular motion is another example of 2D motion. This is, okay, here you go, circular motion. Yeah, let's. Circular motion is another example of 2D motion. Okay. In this case, we can either use the Cartesian coordinate system or the polar coordinate system. In the polar coordinate system, it is easier to describe the motion of the object because one of the components in this system, the radial component, right, is either constant or 0. Okay. So remember, Cartesian versus polar, right? Let's do a table here. I hope you have you seen the polar coordinate system, by the way? Okay, Cartesian. I'm gonna put a table here. Polar coordinate systems. Okay, Cartesian and polar. Okay, the Cartesian coordinate system, you have x and y, right? In the polar coordinate system, you have r and theta. In both cases, they are perpendicular to each other. Those two, you have not? Okay. So let me give you a brief introduction here, how it looks like. Anybody else, can you tell me about whether you have any familiarity with this? No, it's not system, it's symbol.
Wait, so the Q stands for theta?
Well, the what?
The Q stands for theta, or you just need to...
I changed it to theta, see that?
Oh, okay.
Okay, in the keyboard, the letter Q, is the theta when you change the font, okay?
Oh, okay. Thank you.
Okay, so if I change back to, Calibri, see that? It's Q, right? But if I go to symbol, which displays the Greek letters, the Q represents the theta. The same thing, here you go. I'm going to write it down. I hate that. A, B, C, D, E, F, G, H, I, right? And those are all Calibri fonts, right? But if I change to symbol, you're going to see that the A stands for alpha, the first letter of the Greek alphabet. Beta, this one is chi. This one is delta. D is for delta. E is for epsilon. This one is phi, gamma. Okay, gamma is the C. It's supposed to be the C in the Greek letter, but the keyboard doesn't map like that. Here's the A, B, C, D, E, F, G, H, I. I in Greek is the iota letter. J, K, C, kappa, right? L is lambda, okay. M is mu, N is nu, O is omicron. So it maps almost the same from Greek to Latin alphabet, okay? MNO, P is pi, yeah, you know pi, right? PQ is theta, R is rho, S is sigma, T is tau. A Greek student of mine told me this: we don't say tau, we say taf, in Greek. U is I don't know this letter. V, I don't know this letter. X, W omega, Y psi, right? This is the letter of psi for psychology. W epsilon Z. This one must be zeta. Yeah. So it's very, it's very, yeah, see that? The capital zeta appears exactly like in the Latin alphabet. Okay, this is the lowercase zeta, this is the uppercase zeta. So, it's a good idea to memorize some of the Greek letters. But let's go back here, right? Go back here. There is a relationship between those coordinate systems. Okay, for uniform, going back, uniform circular motion, both x and y are a function of t, okay? The advantage of the polar coordinate system is that the r coordinate system is a constant, and the theta is a function of t. That's the advantage. One of the coordinate systems is not a function of t. I'm going to put that like that. F as a function of, f as a function of t, and here g, y is also a function of t, but r is constant, and theta, I will put it h, is also a function of t. Yep.
So, Professor, it's just like f of x, but you replace the x part as t?
Well, well, there are two ways of writing those things. Not f of x. No, it's not f of x. Remember, it's the parametric equation, right? We wrote down the parametric equation before for the projectile motion, and both the x and y can be described as a function of t. And I'm going to show you how to get that. Okay, I'm going to show you how to get that. But recall what we did in the projectile motion. In the projectile motion, we started with the parametric equations for x and y. Okay, x was equal to x naught plus v naught xt, right? That's the parametric equation. Y was y naught v naught yt plus half at squared, right? Half of minus g t squared over 2. So that was the parametric equation. And later on, we moved to the other equation, y is a function of x, right? But in general, we get those are called the equations of motion, right? Equations of motion. Equations of motion. And I'm going to walk you through. So here you go. Here's the x-axis. Here's the y-axis. Okay, and here's the path of your object. The radius is r. Okay, and here is the position of your object. What you see right here is the vector position r. Okay, the vector position r, which by the way doesn't change. And also this is in the polar coordinate system. Okay, polar coordinate system goes from the first coordinate of the polar coordinate system goes from the origin to the point in the circle, and that is a polar coordinate system. And the theta is the second coordinate of your polar coordinate system. Let's see if I have something else here. Okay. Oh, and by the way, here's the relationship between the polar coordinates and the Cartesian coordinates. Right? And let me break it down here into, I'm going to first do the x coordinate. Oh, no. This one here that I want to erase it. Yeah, here you go. That's the x and that's the y. From this triangle alone, we can get a relation between the Cartesian coordinate system and the polar coordinate system. And like I said, the advantage of the polar coordinate system in this type of motion, under the circular motion, is that the radial coordinate, here you go, here we call the radial coordinate, and here we call the angular coordinate. The radial coordinate is constant, but not the angular coordinate, okay? That's the advantage of dealing with this coordinate system, with the polar coordinate system. Let's see, oh, here you go. Here's the velocity vector of your particle. I'm going to do something else here. Let me see if I can do it. Yeah, okay, good. One more thing that I didn't do in this drawing, and I'm going to do before I move for the velocity vector, is that I'm going to show you that by the same token that we have the x hat and y hat in the Cartesian coordinate system, we also have the unit vectors, the corresponding unit vectors in the radial coordinate system. When I say that the the radial coordinate is constant, I'm not telling you the whole truth, okay? What is constant in the radial coordinate is the magnitude of the vector. The magnitude of the vector is constant, but not its direction, because you can see this unit vector r hat changes as time goes by, right? And let's see, I'm gonna display now the theta hat as well. The theta hat, I'm gonna put it here. The unit theta hat. Those two vectors, they are perpendicular to each other. Q, and now I have to change the symbol here. It didn't change. Let's try again. Ah, strange. Very strange. Let's see. I think I know what's the problem. It's like that. Yeah, good. I got it. And I want to change it to red color. This one is going to be changed to red color as well. Good. And let's not forget, you know, we also have the X hat and the Y hat, right? X hat here. And the Y hat. Okay. Maybe I should put it here a little bit higher. Yeah. Note C, remember that the velocity vector is always tangent to the path, right? Always. Doesn't matter which type of path the particle is undergoing, the two-dimensional or three-dimensional space. In the one-dimensional, two-dimensional, or three-dimensional space. Here you go. And here's the velocity vector. The velocity vector is parallel to the theta hat unit vector. It doesn't look like exactly, yeah, it should be. Okay, what else? Everything that you have, you know, the only new thing that you have seen so far here was the r hat and theta hat, right? That's the only thing. Everything else that we have, that you have here, there's no news for you, because we cover two-dimensional motion before. Okay, so here you go. The velocity vector makes a 90-degree angle with the position vector. Okay, this ACP is not supposed to be there yet. Let me erase that. Okay, let's see. Okay, now it's supposed to be there. And then recall that I told you that the acceleration vector always points towards the concavity of the path, and that's exactly what you have here. Because we have a uniform motion, because the speed of this velocity is constant, there will be no component of the acceleration tangent to the path. If there were a component of the acceleration tangent to the path, this velocity vector would be changing. But for the case of uniform circular motion, what's going on here? Okay, because for the case of the uniform circular motion, we have an acceleration vector that's only in the radial direction, but then the radial direction be to the center of the circle. The tangential component of the acceleration in this case is 0. That's why the speed of the particle remains the same. I'm going to write that down. Okay, here you go. So here we have my particle there at the beginning, right? And then keep on moving in circle, okay? Can you picture that? That's that animation, right? If I want, I can put my position vector there as well. Let's put that. Let's put the position vector there as well. This position vector that you see here is going to go here. Oh, but I have to, don't forget, I have to label it as well. Yeah, here you go. I'll label it. Yeah, and then I gotta change a little bit the position of the position vector, right? And I can do that for the other frames of this animation, right? Initially, the position vector is in the horizontal direction, right? A little bit later, the position vector moves. See, the magnitude of the position vector doesn't change, but its direction does change. But it's still an advantage to deal with. Let's see here. Here you go. Starts here. First frame, second frame, third frame, right? I'm going to move my velocity vector a little bit here. Let's see, my particle is a little bit off, right? Let's see if I can do better than that. And my velocity vector seems that it's not exactly normal. Oh, I hate that. Oh, why is, now it doesn't let me get out of here. Oh gosh, how do I close this thing? Okay, now I close it. I'll move this guy out. I'm going to do the following. I'm going to rotate this guy by 90 degrees. So I'm sure, size and position. See that? Size, rotation, right in here. 90 degrees. So that's not what I want to do. Okay, here you go. Now this one, what I want to do. Size and position, put 90 degrees here. Okay, oh gosh, that's not the 90 degrees that I wanted. I wanted 270. Yeah, now that's the right direction. Now I can rest assured that this vector is making an angle of 90 degrees with the radial direction. And I'm gonna move it a little bit here, right? And I don't need that anymore. Good. That's the initial position. In the next position, we have something like that. In the next one, we have something like that, right? That's the movie that you have to keep on playing in your head. And let's not forget, we also have a centripetal acceleration here in this drawing that I didn't do. Okay? So let's go back to our first slide, right? Here you go. And I'm going to document in the notes what I just described here. Anybody else have seen polar coordinate systems here? Yes, I haven't seen, right? What about everybody else? Want to hear from everybody else here. Annabelle, have you seen polar coordinate systems in the past? Annabelle is not answering.
I'm sorry, what happened?
Yeah?
Yeah.
You have seen? Oh, cool. Okay, so let's see. Let me get the attendance, right? Since I'm calling you one by one. I already have attendance here, lecture. Let's see, today is the 23rd. Polar coordinate system, polar coordination. Sky, are you there? Taking attendance. Hello, Sky.
Yes, I'm here.
Okay, have you seen polar coordinate systems before, Sky?
No.
No? Okay. Some of you have seen, other Tessa already told me she hasn't, right? What about Destiny? Have you seen polar coordinates before, Destiny? Destiny is not here. Next is Gael. Gael disappeared, right? Next is Ridwan. I don't see Ridwan here. Oh, very few students today, and only 9. Ashley Izumo. Ashley, are you there? No. Norberto, have you seen polar coordinate systems before, Norberto?
I haven't.
You haven't? No.
No.
Okay, I'm put it here. Anna, Annabelle saw, right?
Yes.
Okay. Yeah, your mic is fading, Annabelle, for some reason. If you could type, it would be better. Vanessa, have you seen polar coordinate systems before?
No, I haven't.
No? Okay. It's usually taught in math. Catherine, have you seen polar coordinate systems, Catherine?
No, I haven't.
Okay. So Camden, have you seen Camden?
No.
No?
I have
Okay.
a question.
Yeah, what's that?
So, velocity and resultant, is that resultant, the R?
The position vector, you're referring to the position vector?
Yeah, I'm referring positional vector and then R. But when since they're moving it together, they're always like 90 degrees, right?
They are always 90 degrees. By the same token that X and Y unit vectors are 90 degrees, the R hat and the theta hat are always 90 degrees as well. Yeah.
And I have one more question. So Cartesian and polar coordinate systems are like meant to be together, or they're all like separated?
They're different coordinate systems, right? So when you use Cartesian coordinate systems, you don't use polar coordinate systems. When you use polar coordinate systems, you do not use Cartesian coordinate system, okay?
But you wrote down x-axis and y-axis. That's why I was kind of confused. Like, if they were like same thing.
Yeah. So some problems are easier to solve with polar coordinate systems than with Cartesian coordinate systems, and vice versa. Depending on the problem, we choose the proper coordinate system to make it easier to solve the problem. Okay.
Okay, so the capitalized R is radius, right?
Oh yeah. This guy here is a scalar, right? And this guy here is a vector, right?
Okay.
Okay. And let's not forget also one more important thing, right? Because in this type of motion, okay, in this type of motion, let's see if I now. In this type of motion, the magnitude of the position vector is equal to capital R, right?
But I have a question. You said the capitalized R is scalar, right? But
Scalar.
but the thing is the vector is with direction, no? How can
That's right.
can we like switch to like scalar to vector or vector to scalar?
Yeah, the magnitude, right? The magnitude of the vector is equal to this scalar. Okay, don't forget it's the magnitude only. Okay, if you were to write another way to do it is for you to see it more easily, it's like that. I'm going to write the position vector in terms of its scalar, right? Yeah. And the unit vectors. Why is not okay? Good. Okay. Here you go. R, see? Big R scalar. Oops. Big R scalar. Let's see if I can. Yeah, okay. Now I got it. Times the hat. the unit vector r hat. Okay, that's what r vector is all about, and that's where this relationship comes from. That's where the
Okay.
relationship comes from. Okay, so going back here, Victoria Preciado. I don't see Victoria here. Alexis. I don't see Alexis here. Marco Sanchez. Are you here, Marco? Preciado. Oh, sorry, Victoria. Yeah, you haven't seen. And Alexis, Marco here. Did you see? Have you ever seen polar coordinate systems, Marco? Okay, most of you haven't seen. Let's make sure that I have the right number of students here. 9. Something wrong here. Let's see.
Professor,
Yeah.
I have one more question. So, polar coordinate system, is very common coordinate system to use in circular motion. That's
Yeah.
the okay.
Yeah, that's right. You know, the first coordinate system that we study is the Cartesian coordinate system. That's the very first one that we study. And then further down the line, we study the polar coordinate system. And then further down the line, we study, let's say, the cylindrical coordinate system, which is an extension, which is the three-dimensional counterpart of the polar coordinate system. And then further down the line, we look at the spherical coordinate system. Okay.
So polar coordinate system is 2D motion, right?
It's 2D motion. That's right.
Okay.
Okay, so let's write it down. There are no, let's see, before Sky is here, right? Destiny. Okay, Destiny is not here. Why did I put 0 here? Oh, wait, sorry. Tessa. Destiny, Tessa. Norberto is here. Annabelle is here. Vanessa is here. Catherine is. What happened to Catherine? Looks like Catherine left, right? Oh, Catherine was not here. Oh, I see. Catherine was not here. Okay, Camden is here. Victoria is here, and Marco Daniel. Okay, good. Now we have the right number here. And okay, so let's go. You know, coordinate systems. Coordinate system. You know, coordinate systems to know, right? Cartesian coordinate system. And polar coordinate system. Oh gosh. Here for the Cartesian coordinate system, we have the 2D, right? Coordinate system that is X and Y, and we have the 3D Cartesian coordinate system, the X, Y, and Z. And polar coordinate system. Then for the 2D coordinate system that described by the r theta coordinates. Combo. Good. In uniform circular motion, the polar coordinate system is more convenient to use because the magnitude of the position vector is constant and given by the radius of the circle r. That's what r is all about, is the radius of the circle.
Professor, I have a question.
Huh?
So I Googled polar coordinate used in real life,
Uh-huh.
and I found out that polar coordinate system is very useful when it comes to satellite navigation systems like GPS, right? But satellite is 3D
Yeah.
motion based I don't know, like coordinate system, no?
You gotta give me the link for this website. Can you send the link me through the chat? It doesn't make much sense, right, to say that they use polar coordinate system for GPS because the satellites are in the three-dimensional space. Most likely, he meant the spherical coordinate system. Study real life.
Oh, yeah.
Okay.
Oh, I mean, I just Googled it because like I was wondering how do you use this in real life? Well, so
Uh-huh. I don't think they use polar coordinate system for GPS. Okay, I think that they use the spherical coordinate system. Let's say polar offering perspective problems and angles. This guy that will walk for polar coordinate. Elucidate, let's say, step-by-step guide to learn about grasping the basic polar, delving into the mathematics, exploring the role of polar. Where do you see that for GPS? Okay, must be here, right? Polar coordinate for the geographic coordinate systems used to pinpoint. Okay, yeah, that makes sense. Let's see. Polar coordinate from the basis of for geographic coordinates used to pinpoint locations on Earth. Understand how longitude latitude can be seen as a type of polar coordinate. Additional navigation, especially maritime navigation, bearings are used to indicate direct. I don't quite agree with him because latitude and longitude. What would be latitude and longitude are two different angular coordinates. Okay.
So
And
when they all operate the satellite system, they're using this 2D motion systems to input the values and calculate the final output value. That's how it works.
where do you see that? Where do you see
No,
that?
I mean that's my guess. Like I'm just guessing this.
Well, he's not. I don't agree what he wrote here. Okay, it's he's telling part of the story. Okay, he's just telling part of the story. Apparently, this guy here didn't quite understand, didn't quite explain well what he was supposed to explain. Okay, what actually happens is that the satellites that are orbiting the Earth, okay, and those the satellites that provide the information, the geographical location of anybody, anything in the Earth's surface, those satellites, the orbit of those satellites can be described in terms of polar coordinate system, the orbit of those satellites.
Yeah, okay? Because it's like circle, right? It's like, well,
it can be circle or it can be elliptical. Okay, can be again, and we're going to cover that, okay? Can be either circular or it can be elliptical. The orbit, yes, is a two-dimensional motion. The orbit of the satellites, yes. Okay. The motion of any planet or satellite is a two-dimensional motion. The Earth doesn't move in 3 dimensions when it goes around the sun, okay? It just stays in a single plane. The moon is the same thing. The moon stays in the single plane when they move about the Earth. That's a nice feature of orbital mechanics. That's a nice feature of orbital mechanics, which simplifies a lot the treatment of the motion of satellites. Now, to go the next step and saying that we use a polar coordinate system to locate an object on Earth, that's incorrect. That's not correct, okay? That's not correct because now we are dealing with the radial distance from the center of the Earth, okay, of the object, plus the latitude and the longitude, which are two different angular positions, angular coordinates, okay? So to locate an object on the surface of the Earth, we do not use the polar coordinate system. We use the spherical coordinate system, which is the radial position from the center of the Earth, the azimuthal angle, which is the latitude, right? And the polar angle, which is the longitude. the longitude, which is 90 minus the longitude. Okay.
Oh, okay.
So that would, so when he said polar coordinate system, that's not quite right. Okay. He apparently this author here is mixing up the motion of the satellite in space with the location of an individual on the surface of the Earth. He should have written the instead of polar coordinate, he should have written spherical coordinates. Spherical coordinates. Okay.
How do you spell that?
Spherical, just like a sphere, just like a sphere. Other, I'm gonna write that down here. Here you go. Other, let's see, other coordinate systems. Other coordinate systems. 3D polar, also referred as cylindrical coordinate system. In the cylindrical coordinate system, we have the r, the theta, and the z. Okay, r, theta, and z.
So cylindrical coordinate system is just z combined
with r and
with.
theta.
Oh, okay.
Okay, and then the 3D, and then the other one, another 3D, the 3D spherical coordinate system, which is r, we call it phi, and then we call it theta. Let's see if that's the right one. Symbol.
So spherical coordinate system is, you said, what is that called? Latitude combined with
longitude.
longitude. Oh, okay, okay.
Yeah,
Oh.
yeah. This one should be the longitude. This one here should be the 90 degrees minus the latitude. Okay.
Oh, okay.
Yeah. But wait a minute. Yeah, that's right. 90 degrees minus the latitude. Latitude is equal to 90 degrees minus theta. Minus degree minus. Okay, that's what. That should be the longitude. That should be the latitude. Okay, but we're not going to cover those two. Okay, so let's go back here. Uniform circular motion, the polar coordinate system is more convenient to use because the magnitude of the position vector is constant and given by the radius of the circle r. Okay, because of the following. Here you go. Because of the following. Here you go. I'm gonna put because of the following. One, the magnitude of the position vector is constant and given by the radius of the circle. Two, okay, the tangential velocity is parallel to the theta coordinate. The unit vector along the theta direction, right? The tangential velocity is parallel and is constant and parallel the unit velocity to the unit vector along the theta direction. Okay, the radial component of the velocity is 0, right? Compare that with the Cartesian coordinate system. You have a velocity along the x direction and the velocity along the y direction, right? The tangential acceleration is 0. And finally, the radial component of the acceleration is not the radial component. The radial component of the acceleration is constant, and we're going to show that with the component, not the acceleration itself. The direction varies, although its direction varies, right? The same thing, the magnitude of position vector is constant and given by the radius of the circle. Although its direction, right? The direction of the position vector, its direction varies, right? So let's try to compare one with the other, right? Let's see if I can. Cartesian UCM, UCM in Cartesian versus polar coordinate. In Cartesian versus polar coordinates. Coordinates, right? Let's see, Cartesian. Let's see here, position. Position is described by the coordinates x and y, right? X is a function of time, and I'm going to show you very soon. Let's see. Ny equal g of t, right? G of t r 1, 2, 3. I have to trick, right? And theta is a function of t, okay? Position. So I'm just copy and paste what I had here before, right? Velocity. V sub x is also, let's see, FGHI. J, I'm gonna put is also a function of t. B sub, I'm gonna put it k now is also a function of t. Notation, right? That's a notation. V sub r is 0, right? V sub theta is constant. See the difference? And then finally we have the acceleration. 1, 2, 3 ax. Now L of the function of t, right? I'm running out of alphabets in the letters in the alphabet. A sub y, m of t, right? Is a function of t. 1, 2, 3. Acceleration in the radial direction is constant, and acceleration in the theta direction is 0. And now I can make those things look nicer, right? Don't forget the subscript. That's notation wise. Now do you see? Now it's easier to see why it's so convenient to use the polar coordinate system, right? Everything here is a function of t. And here, only one component is a function of t. See that? Only one component. The component is a function of t, not the direction. Okay? However, so there is a, there's something interesting here. Although the components, although we have only one component along the theta direction, that is a function of t, comma, the unit vectors along the radial and angular direction are a function of t, okay? So you have a simplicity here, but then you have a little complication elsewhere, right? In terms of the scalar components of the polar coordinate, they are simpler than the scalar components of the Cartesian coordinate system, but the direction in the polar coordinate system, they're always changing, whereas the direction of the x hat and y hat, they are always constant. Direction, okay? Direction.
I have a question. What is J of t and K of t?
It's a notation for function. Okay, do you see that? I put a notation for function here. Function as a function of t, right? That's the notation that we use in mathematics, right? G of t is another function as a function of t. And then I started using, expanding in the
So-
alphabet, right? This is another function.
It's just constant, right? It's just variable.
No, it's not constant. Those ones are
No?
variables. Those are functions of t, okay? Function of
Okay.
t, right? What is constant are here, right?
The
Always
polar coordinate system has only two things to remember, which is like R and V. That's all you
R
need
and
to.
theta.
R and theta, right? R
R
and
and-
theta. Oh,
Yeah.
okay.
R and theta. Just like the Cartesian, right? You have to remember only x and y.
Hmm.
You have to remember only x and y. Always constant, but direction changes in time. Okay, so somewhere you have to give in the polar coordinate system, right? It's not everything that's simpler. Something is more complicated, and something that's more complicated is the direction of the vectors, direction of the components of the vectors. That has to be, that has to change as time goes by. And oops, another one. This one, another one. Here goes. Positive velocity acceleration. That's a nice table to keep in mind. And now let's see how one relates to the other, right? 952. Let's see if we can do that. Okay. Notice that those r hat and theta hat, they change direction as they go around the circle, right? They change direction as they go around the circle. So let's see, 953. Let's take a little break now. So I think it's a good spot to take a break and break. And then we're going to elaborate a little bit more from 9:55 a.m. to 10 a.m. Any questions before we proceed? Okay, but do you know, Sikandar, that sometimes we don't get the right information there in the internet, right? It's so easy to publish in the internet nowadays that some people publish things that are not completely correct. When I look at that, it occurs to me that this guy is mixing up the position of the satellites in orbit with the position of an object on the surface of the Earth. Okay, so yeah, so yes, the motion of a satellite in orbit is a two-dimensional motion, yes, but not the motion
Not the coordinate system.
Yeah, not the motion of an object on the surface of the Earth.
Oh, okay.
Okay, so
how do I find the legit information from internet? Do I need to?
That's a good question. Yeah, you have to cross-check, right, from other sources, right, and then make your own decision, right? You have to cross-check. Maybe you might want to look at Wikipedia,
Mm-hmm.
do a search on polar coordinate systems on Wikipedia or some other. That's the way to do it. You know, that's the way
Okay.
to do it. Because it's really bad if someone puts something in the internet and then someone who has never seen that reads it and believes it, right?
Mm-hmm.
And I have seen that more than once. Students were taught the wrong information. I have seen that more than once.
So should I just like use like institute websites to get the information like when it comes to this kind of thing? Like
Yeah, and also do the cross check as well, right? Cross check as well. You know,
Okay.
check with other sources to see if
Mhm.
it matches what the other one is talking about.
Okay.
Yeah, that's yeah, T is time. Yeah, this asked is T is time. Yes, there's a T is time. Okay. Okay, so let's go for a break. I see you in 15 minutes.
All right. Thank you, Professor.
Welcome. Okay, I'm back here. Okay. Now I'm going to do the detailed mathematical approach for this problem, right? And some of it I'm going to repeat what I put there on the table. Okay, so it's like that. This one is obvious. This one is obvious from the fact that we have circular motion, okay? The above is obvious. Due to the fact that we have circular motion, right? Where the circle has a constant radius. Okay, the same cannot be said about projectile motion, right? Do you remember about projectile motion? Let's go back to projectile. Oh, here you go. Here's the projectile motion, right? Not this one. I don't want this one. I want this one here. Look at the projectile motion. The magnitude of the position vector is not constant. It's not constant, right? At a given instant of time, the magnitude of the position vector is this one, magnitude is this one, magnitude of this one, right? Magnitude is this one, changes, right? The magnitude of the position vector changes as time goes by, but not for the case of for circular motion. And it doesn't matter if it's uniform or not. If it's circular motion, the magnitude of the position vector does not change. Okay? Now, if you add to the definition of the motion that the motion is uniform, okay? If you add to this type of motion, that it is also uniform, right? What uniform motion means? Uniform means this means the following. This means the following: that the magnitude of the velocity vector is constant as well. Okay. And in terms of the Cartesian coordinate system, we can write something like that. Okay? In terms of the Cartesian coordinate system, the x and y components of the position vector can be written in terms of r, v, and t. Oh, we're gonna get r. I'm gonna put here r and theta, right? First r and theta. Let's write in terms of r and theta first, and then we worry about how we write theta in terms of t. Okay, I'm going to eliminate this functional dependence on t right now, just to simplify. Going back here to my uniform circular motion, right? Here you go. The x coordinate system, right? X divided by r is cosine of theta, right? X divided by r, I'm going to put it, like that. And similarly, we have y divided by r is sine of theta. R and R. X, okay, like that. That's obtained from the drawing. The above is obtained from the illustration. But we still do not have a parametric equation, which involves the time, the variable time.
Professor, is this chapter 3?
No, it's chapter 5, right?
But chapter 3 has similar
Let me
materials
see.
like that. No?
Let me
I mean
see.
chapter 3 homework.
Oh, most likely they were advancing. Sometimes they do that. Chapter 3. Sometimes they do that. Okay. Sometimes
Okay.
they advance the material in the homework. Sometimes they do that.
Okay.
Which homework is that?
The number 1, but
Uh,
I was just wondering.
yeah, number 1. You mean the homework
Number
in the book, or in the homework of that I posted?
assignment homework,
Huh?
not from the textbook.
Not from
From
the text.
the wildlife.
Okay, the one that I posted. Okay.
Yeah.
Okay.
I was just wondering.
Yeah. Like I said, sometimes the book does that. Sometimes the book does. I have seen that over and over again. They give a problem that is going to show up in the next chapter, right? But just as preparation for the student on before the chapter is introduced.
Okay.
Okay, so here we go. And by the way, uniform motions is very important. Okay. And let's see, the question now is to find the parametric equations for x and y, okay, i.e. as a function of t, okay? And we can do that again by referring to the drawing. We can do that, and we can do that by referring back to the drawing. Okay, and let's go there. Here you go. You saw that, right? You also saw this animation, and in this animation, you also saw something else. You saw here the path length S of the object in the circle. Okay? This object, moves a given distance here along this arc. And there is a relationship for S, R, and theta. There's a relationship for those three. And the relationship is the very definition of angle. How do we define angle? Okay, I'm gonna show you how do we define angle. Referring back to the drawing. The drawing here, we notice that we have a relation between the distance traveled along the circle, and I call this distance S, the radius of the circle R, and the angle theta. Like that. Here you go. Here's the relation. That's the very definition of angle. Is the arc length divided by the radius of the circle. What comes next is even more interesting. What comes next? No, I remember I just erased that, right? Because I want you to think a little bit about that. It's even more interesting because don't forget, travel along the circle. The above is the very definition of an angle. Okay, and I don't want to miss this relation here, but don't look at that yet. Okay, what I'm going to do, I'm going to substitute the relation for the angle right here. Right, here you go. Right here. And the next question, how do we find S? Okay. Well, this parameter follows naturally from the very definition of the type of motion. Don't forget this uniform motion. Okay? Because it is uniform motion, S must be V times T, right? Every time that you have uniform motion, we have constant velocity, and the displacement is going to be the velocity times T. And now here we go. We have we can replace VT right here for S. VT right here for S. And you have the equations of the motion for the position. The parametric equation. And we also have the equation of the motion for the coordinates, right? In the polar for the coordinates. Here you go. R. The coordinate R is going to be equal to R, which is a constant. And the polar coordinate theta, which is this one here, is going to be given by VT over R. Okay. What comes next is not all the equations of motion that we want, right? You already know. You already know that that V sub R, right? The velocity along the radial direction is going to be 0 because it is a circular motion. What is not so obvious is the theta component of the velocity. The theta component of the velocity is going to be v over r. That's not obvious, okay? But just remember that. Okay, we can even say, I can even go another step here. Instead of saying, the theta component of the velocity is going to be something like that, delta theta over delta t, right? If the velocity along the x coordinate is delta x over delta t, the velocity along the theta coordinate is going to be delta theta over delta t.
I have a question.
Yeah.
How do you calculate delta theta? Like,
Oh.
do you initial data? I mean, the final delta minus initial theta.
Yeah, that's right. Final theta, right? I'm gonna put here you go. Minus initial theta naught, right? And don't
Okay.
forget, so it's gonna be t minus t naught, right? Now, if we set theta naught equal to 0 at time t equal to 0, we have something like that, right? So we have the angular velocity, we call that the angular velocity. But this angle, we already found out that's Vt over r, right? Vt over r. We cancel t with t, and what we get? We get v over r. That's the angular velocity. Okay. So just like before, just like I mentioned before, right? The theta component of the velocity is a constant, and I'm gonna put that here, constant. I'm going to emphasize that's constant. And now we can start building our table, elaborate on the table that I was building before, right? We'll elaborate right here.
Professor, but the times are gonna be given, right?
Yeah, the time is the parameter, right? Is the parameter, is the variable, is the parameter. Okay. So Cartesian, let's see, position. I'm gonna do like that. I'm going to, let's see how I'm gonna do that. I'm gonna break it down into 2 lines. Let's see if I can do that. Split cells. I need to split in 2 rows and 2 columns. Okay. Coordinate X, coordinate Y, right? I'm just elaborating what I did before. Okay. Position. And I already found it. It's something like that. And I'm going to emphasize that this X, both X and Y are a function of T. And it's not, you know what? I need to do better than that. I can do better than that. Let me split this one instead. Split cell, 2 columns. No, it's 2 rows in 1 column. 2 rows, yeah. This one is gonna be 2 columns. Two column, good. Okay. X component, I'm gonna put that X component. And here I'm gonna put Y component. Okay. And this one is gonna remain what we had before. This one is gonna remain what we have before. See, I'm building a table in the best possible way And it's very important that in the future you also learn how to organize information in this manner. It's a very difficult, by the way, it's a very difficult skill to have, okay? Organize the information in a table.
Professor, I have a question.
Yeah.
Okay, so when it comes to polar acceleration, let's say the acceleration is going towards negative direction, then do you have to apply the gravity or just
No, there's no
no,
gravity
right?
there because it's a horizontal surface, okay?
Horizontal?
It's not,
Oh, okay.
it's not subjected to the acceleration of gravity, okay?
So polar coordination acceleration is always horizontal.
For this specific example that you are dealing, okay, the acceleration of gravity doesn't affect the problem for this specific example that you are dealing. Okay.
Okay.
There will be other examples, okay, in which the acceleration of gravity will affect the outcome of your problem. Yeah. In other examples.
Okay.
There will be. But in this case, you know, the X and Y is horizontal, and then the Z axis, you know, is sticking out from the plane here. It's pointing towards you. And the acceleration of gravity is just into the board, okay? If you were to draw the three-dimensional space. Another drawing would be this one here that you see. See that? This here of the kid, you know. This circle here that he's describing with the airplane is in the horizontal plane.
Physics.
Okay, in the horizontal plane. And going back. Okay, here, polar. And then I'm gonna do the same here. Split cell. 2 rows, 1 column. 1 row, 2 columns.
Huh. So
yeah. 1, 2, 3 R component. 1, 2, 3 theta component. Theta component and symbol. Coordinate systems Cartesian. I think I wanna keep this, and maybe I want to do even better. Yeah, as we move on, we discover better ways of drawing this table. I'm going to split it again. Here you go. Coordinate system, right? It's going to be 2 rows and 1 column, and then I'm going to write down here components. See that? And now I don't need to write the component for X and Y or R and theta, right?
Professor, so this is the finer form for the
yeah, that's a fine, more detailed.
More detail? Okay.
Yeah, compared to what we had before, right? Here's a function of time. Now I'm telling you exactly what the function of time is. Okay, what the function of time is. Going back, right here, we do the same thing. Split cells, 2 columns, 1, yeah, right that. Okay. And now this, I already put it, the big R, capital R. Here, what I put, we found out what the theta was, right? Theta is VT over R. I think I got one more. Nah, it doesn't look good, right? Here you go. The velocity, similar. Let's see, the velocity is going to be, okay, to find the velocity in the X and Y direction, it's a little bit more complicated, but let's at least, you know, write down the radial velocity, right? The value of the radial velocity, which is 0, and the value of the angular velocity as being v divided by r. Now here's a little bit more difficult. Let me erase that. I will split that into two cells, two columns. And then we have to look at our vector here, our vector velocity here. That's what we are going to look at. And I will come up with some more details. Okay, this vector velocity has a x component and a y component. Right? Everybody see that? This
Yes.
vector velocity has a x component. I'm even going to use a right angle triangle that we have here in this pad to get a better, okay, here you go. Hopefully I think I got it, right? Yeah. Here's the x component. And I'm going to, I think, just shorten a little bit, right? And now we can draw the y component. And I'm going to dash it. Dash and let me see here. Doesn't look, oh yeah, my x component is not quite right, huh? And that's because my right angle triangle is not quite right either. But I think I got it now. Yeah, I think I got it now. No, not yet. What about now? Yeah, now we got it. Okay. Okay. I'm gonna dash this guy as well. It's very important that you do the same thing right by hand, right? This angle here is theta. So this angle here must be theta as well. Okay. I think I have the angle theta somewhere. Oh yeah, this one. I have the angle theta right here. Where is that? This one. Yeah. If this angle here is theta, this one also must be theta. If this one is theta, this one is 90 minus theta. If this one is 90 minus theta and this one is 90, so this one must be theta.
Professor, which one is the theta?
This one right
With-
here.
No, I mean the other from the. No. I mean, what's that called? The red triangle, the right triangle from there.
Here you go. Step by step, right? Here you go. Step by step. This one is theta.
Yeah, and then.
Okay, and then let's see. Let me get this guy right here. So I have everything lined up perfectly. This one must be theta as well.
Oh,
Right?
okay.
The z, right? The little z. Oh man, I erased it. Oh gosh, I hate that. Put it back there. Here you go. Theta. Theta. And I can even extend this thing, right? And take out the arrow. Here you go. So it's easier for you to believe that. If this one is theta, This one must be theta as well, right? We usually, how do we denote that in math to simplify? We usually put a little dash here, right?
Mhm.
And then we put the same dash elsewhere to simplify the drawing. And now I don't need to put my theta there. One dash here, one dash here. Okay. Now, if this angle is theta and this angle is 90 degrees, right? This angle here is going to be 90 minus theta. Everybody agree with that? This one
Yeah.
must be 90 minus theta. Okay? And if this one is 90 minus theta and this one is theta and 90, then this one here must be theta. So I'm going to go ahead and place it right in here. Whoa. Whoa. And we go ahead and put another dash in there. Right? Like that.
So they're all sharing same values, right?
Yeah, the same angles. They're all the
Same
same
angles.
angles. You know, making my angle smaller, right?
So 3 thetas are the maximum from the unit circular motion
What's that?
diagram. So you're describing that there should be 3 thetas in the unicircular motion body
Yeah.
diagram, right?
That's right. There
But
is
that's
a
the maximum.
yeah. There's a theta angle here. There's a theta angle here, and there's a theta angle here. Okay.
That's
Why
the
am I
maximum
doing
number.
that? Why am I doing that? There's a reason why I'm doing that. Okay. I'm doing that because I want to find out what's the x component of the velocity and what's the y component of the velocity, how we can write them out. Okay, that's why I'm doing that. Okay.
So that's the maximum thetas you can have from the quarter circular.
No, the maximum theta is 90 degrees, right? It's 90 degrees, right? Oh, can be even 100. It depends what you mean by maximum, right? Theta can go anywhere between 0 and 360 degrees. So strictly speaking, theta can be 360 degrees. That would be the maximum value. Those
No,
are
I'm not talking about the degree. I'm talking about maximum amounts, like thetas that you can have in the like a quarter circular, the unicircular motion.
Let me see here. Okay. Well, maximum amount. Well, I do not know what I mean by maximum amount, but what I want to find out here is those angles here, so you can find Vx and Vy. Okay, that's what you have to concentrate right now.
Oh, okay.
Okay, so let's take a look. Okay, Vx is going to be, V sine of theta, because it's opposite to this angle here. Okay, so here you go. And then I will have to do, let's see. I will do it where I'm gonna do. I'm gonna do it here. I'm gonna do it here. Vx over V is going to be sine of theta. But let's not forget that theta is Vt over R, right? Vt over R. And we have something similar. Oh, by the way, there's one more. it must be minus because the component points to the left. The component points to the left, so you must have a minus sign there. And we have something similar for the y component. Instead of sine, it's going to be cosine, right? Okay, so must be out. Gotta carry this sign, negative sign here, right? We get that. Vx, vy, v. That's exactly what I'm supposed to get. I did the r and theta coordinates because they were easier, right? And here we go. All I have to do is make it v. Is that v? Let's see here. Vx. Yeah. Yeah, that's right. V sine is a minus sign here. And now all I have to do is copy, paste it. Yeah. Oh, wait a minute. Oh, yeah, see, it's supposed to be sine. Why did I put cosine there? Nobody picked that up. Huh? Here you go. Yeah, I had sine in there. Here should be supposed to be cosine. So we got it. We got the velocity, the x component of the velocity and the y component of the velocity. Okay, and then we are left with this acceleration here. I'm gonna break it down into split cells, columns. This one's gonna be easy, right? Split cell. Here, for sure, is gonna be 0. But we do not quite know what's gonna be a sub r, okay? That we have to calculate. And there is a way to calculate it. We are gonna do it. Let's look at this one first. Let's look at this one first. And recall, let's see, go. That would be the direction of the acceleration vector, right? I'm not going to derive here. It's better to derive here, okay? But the way, well, the x component, here you go. The x component of the acceleration is going to be something like that. Let's see if I can get a better drawing of the x component of the acceleration. Yeah, okay. You know, that's the acceleration vector towards the center. You know, I'm going to put it here A instead of R. I don't know why I had R in there. Theta and theta, right? The x component of the acceleration is going to be the magnitude of this vector times cosine of theta, right? Theta and theta, x component, but we must have a negative as well. Okay, now x component, and I'm gonna use this one here, those two. And all I have to do is to change the letters. It's going to be a negative here, but it's going to be not R, but it's going to be something else that I still do not know, that I call it A. And the Y component is also going to be a negative here. It's negative Y because the acceleration is towards the center, whereas the vector position is away from the center. Okay? So the key now is to find out what this value is. Okay? Let's see if the book has. I don't want to do that because it's too lengthy. Okay, it's centripetal acceleration. Let's see if the book does. Yeah, the book does. I want you to look carefully, okay? Delta V over delta T is going to be the acceleration. And the formula is a very easy one to memorize. Is this one here, V squared over R, okay? So my where, you know, look at the book, how to derive A, which is given by, you know, there are how to derive A using graphical techniques, okay? Graphical techniques. This A is going to be given by V squared over R. V is uniform, consequently is constant, right? R is a circle, so it's also constant. And now we have the following for the acceleration. We have a negative sign, V squared over R, a negative sign, V squared over R. Okay, this term, the above term, is called the centripetal acceleration. Centripetal. Centripetal means, which means acceleration towards the center. Okay, we also have what is called centrifugal acceleration. I'm going to emphasize here the difference, right? Centripetal and centrifugal acceleration, which means acceleration away from the center. Okay. And by the way, the R component, remember, going back here, I told you that there is just a radial component for the acceleration. Consequently, this radial component of the acceleration is going to be V squared over R with a negative sign. And always remember, the direction here is constant, X hat and Y hat are constant, but R hat and theta hat are not constant. That's the, you know, that's what you pay for having this simplicity here for the scalar components, right? The vectorial components, they change, whereas the scalar component, most of the scalar components are constant, either constant or zero. That's the price you pay. The price you pay for all the simplicity is that the vector, unit vectors, are not constant. Changes in time. So here are all the description that you need for the equations of motion. Okay, versus polar coordinate equations of motion. Let's put it this way. Equations of motion. I think I'm gonna do better here. Instead of putting x and y components, I'm gonna put unit vectors. Okay. See
Professor,
yeah.
I have a question. So, do we need to use the polar coordination equations or the Cartesian equation
Both.
in order to find both? Oh, okay.
Both. Whenever you find it's more, convenient, you use one. Whenever you believe it's more convenient, use the other.
But polar coordinate is meant to be more convenient, right?
Well, it's meant to be more convenient only for the components, right? Only for the components. But because the r hat and theta hat, they change in time, right? They change in time. Changes their directions, right? Directions change in time, always constant. Like I said, you pay a price for having this simplicity here, right? And the price is to have a change, is to have unit vectors that change in time because of their direction. Okay. What time is that? 10:56. Let's see, read one is here, right? We have 10 students now. Okay, someone else is here. Let's see, read one. Read one, Harrison. Okay, read one. Did you see polar coordinate system before? Hi, read one. Did you see polar coordinate systems before? In the past, in your math class? Most likely not, right? Okay, I'm gonna put that in here. I can't hear your answer. And there is one more student here, right? That's Victoria. No, it's not Victoria. We have 10 students, which is the 10th student. Let's see, Destiny is here. No. Gael is here. No. Ashley is here. No. Catherine. Oh yeah, Catherine is here. Hi, Catherine.
No, I haven't.
Oh, okay, thank you. Okay, so that's 10:58 right now. Okay, let's put this.
Professor, I have a question.
Yeah.
So since polar coordinate is horizontal, in order to find the acceleration, I just need to use this formulas that you wrote on the notes, right? The negative velocity square over r, right?
That's right. That's right. And how do you're asking about this one here, right?
Right.
Yeah. And how do you find that? Your book spells out how you find it. There's a graphical, there's a graphical way of finding that out. And I'm not doing that because it takes too much time. And it starts right in here. See that? So it's a very
it
method.
follows by the V and R, right? That's how you determine if whether, I mean, that's why it's always horizontal, right?
Yeah, it's spelled out here. See centripetal acceleration? Here's the vector velocity, right? So they put together those two vector velocities. See? Because it's a very interesting technique that they came up with. And the lengths of those two vector velocities are the same because it's uniform motion. Okay? If this one is the initial velocity, this one is going to be the final velocity. Remember that acceleration is delta v over delta t. So what you end up having an acceleration vector that's from the right to the left. The delta v is this vector here. Okay.
But it
Yes.
doesn't matter where these vectors located, right? It must be horizontal no matter what, right? When it comes to polar coordination, right?
Well, it's not necessarily horizontal. It's a planar coordinate system. This plane can be either in the horizontal direction or in the vertical direction, okay? However, for this specific problem that we're treating, yes, the motion is in the horizontal direction, okay?
So you can actually indicate the direction, but at the end, the formula must be the same, right? That's what
Yeah.
you're trying to say. Oh, okay, okay.
That's
But
right.
when it comes to Cartesian, you need to apply, like, let's say you need to, if you want to apply an x direction, then you need to use cosine. Or if you want to find like y, then you need to apply a sine. That's what's different. Okay.
That's right. That's right. Yeah. No. Yeah. It's you can see right from that table that yeah, you have the cosine and sine here, sine and cosine here. See that? Whereas here you don't have any cosines whatsoever. See how
Yeah.
simplicity that we
That's
have.
why I was wondering what at the end, like when it comes to like acceleration, it's like almost same as the Cartesian formula, but it just does not indicate any direction or anything. That's why I was wondering.
Okay. 11:01 right now, and so let's see here. Let's take a look at the book. Yeah. Okay. So that's the derivation for the centripetal acceleration. Okay. And we have, let's see, we have 4 more minutes before we go into a break. Let's take a look at this example. The bobsled track at the 1994 Olympics in Norway contained turns of radii 33 meters and 24 meters. Okay, 33 meters is this one. Where's the 24 meters? That's the 24 meter here. Bobsled, right? Find the centripetal acceleration at each turn for speeds 34 meters per second, a speed that was achieved in the 2-man event. Okay, so let's do this step by step here. Let's see if we can do that in 3 minutes. It's very important to have a numerical idea of the accelerations, especially in this case, in which we have athletes moving very fast with their bobsleds and at turns that becomes ever tighter. Okay, turns that become ever tighter. Try to picture yourself inside your car at one of those exits of the freeway, right? Every time that you go at those exits of the freeway that has a very sharp turn, you feel some sort of a force pressing against you away from the center of the curve. That's what we call the centrifugal acceleration. The tighter the curve and the higher the velocity, the stronger the force that you feel inside your car. Okay? And that's what the centripetal acceleration tells you. That's one of the practical applications of centripetal acceleration. And you're going to see what's going to be the acceleration in this case. You know what? Let's see, 2 more minutes to go. I'm gonna just, all you have to do is to substitute 34 meters per second for the first radii, which is 33 meters, right? And what do you get? Let's take a look. Oh, it's 34 meters per second square. Okay, the 35 meters per second square. 35 meters per second square is 3.6 times the acceleration of gravity. That's the type of force that you feel. It is as though as you have 3 times the weight of your body propelling to the left. It's a lot. 3.6 G is a lot. You have to be in very good shape to stand something like that. That's why those guys are athletes, right? And the other one, the radius that's even tighter than that, with the same velocity, is even higher. It's almost 5 Gs. 5 Gs, you're already coming to the point where you can pass out, gray out. Okay? Formula One drivers also are subjected to this type of acceleration in their cars. If you're flying your airplane, doing aerobatic maneuvers, you are also subject to those types of acceleration. Astronauts, when they return from orbit, they sometimes are subject to that too. In the early times of the space flight, the Russian spacecraft, sometimes they were subject to 9 Gs, okay. And fighter pilots are subject to something like that too. Okay. 11:05 right now. So let's take a break. 11:05 to 11:20 a.m. Any more questions before we go for a break?
I have a question.
Yeah.
So, it's about these two acceleration types.
Mm-hmm.
So centripetal acceleration is like going towards the center?
Yeah, that's right.
Oh, okay. So, what about the other one? Centrifugal.
The other one is centrifugal acceleration, okay?
Away from the center.
Yeah, away from the center. Whenever we're going to cover that in more detail, the difference between centripetal and centrifugal acceleration has everything to do with accelerated frames of reference, okay? No inertial frames of reference. I'm going to elaborate a little bit more on that, okay? If you are right now in our referential system, the acceleration of those guys are centripetal because they are moving in a circular path here, and we see their acceleration vector as being pointing to the center. But for those guys in their own referential system, which is accelerated, by the way, our referential system is not accelerated. What do they feel? They feel that they're being thrusted away from the center of the circle. They feel a centrifugal acceleration because their referential is different from ours. Okay, so
But do they have different formulas?
no, the value is the same. The centripetal
values are the same.
acceleration equation is going to be exactly the same as the centrifugal acceleration. It's only the direction. It's only the direction.
Oh, okay, okay.
Only the direction that contrary to each other. Okay.
Okay, thank you, Professor.
Only the direction that's different. Let's see, 11:07. Okay, another question before I go into the break. I'm going to adjust here our break. 11:07. 11:08. Here you go. Let's get one more minute here. 2:22, right? 22, no, 23. So I see you in 15 minutes. Let's see, stop sharing. Okay, so there's a very easy way to memorize those equations, right? Here you go. I'm gonna emphasize that's a positive. That's a positive. Okay, note, see how it evolves, right? Positive, negative, negative. That's how it evolves. And then we have positive, positive, and negative. Can you remember that? If you know that for the position is a cosine, for the velocity is going to be a sine, for the acceleration goes back to a cosine. If the y component of the position is a sine, it means that sine and cosine, they switch it, right? Sine to cosine, cosine to sine. The argument, they are all the same. Okay, they're all the same. The only thing that, and the thing that change as well is going to be the coefficient here, right? Here, this guy is proportional to the position, right? It has to be. This one has to be proportional to the velocity. It has to be because it's the velocity. And this one is proportional to the acceleration, right? It has to be. Plus, minus, minus, plus, plus, minus, right? Cosine for x, sine for y. And then as you move to velocity and acceleration, you change the cosine to sine and the sine to the cosine. It's not that difficult to remember, right? What? And then we have, that's another, let's see. Oh yeah, now we're gonna talk about centripetal force. But before, let's see, we have half an hour to go. Centripetal force, let's see, blanket curve. Yeah, there's quite some material here in chapter 5. We won't be able to finish it today, okay? And there are some other interesting material that I didn't cover yet of the previous chapter. Let's see if I have it here. Examples, right? That I didn't quite cover. We saw that. Okay, yeah. What I want to do first, I want to cover here an example that I didn't do for Newton's second law. And then we go back to, it's a very interesting problem, a very interesting example. And then we go back to the circular motion, okay? So consider someone is standing in a scale, over a scale. Yeah, this guy is not centered quite there. Let's see. Almost there. Oops. Here you go. Now I should have it. Okay.
Is this chapter 4?
This one is going to be chapter 4. Yes, on forces. Yes, laws of motion. Yeah. I'm going to do some examples here of chapter 4, and then we go back to chapter 5 to make some to do some examples. Your work will have to be later on 6, 7. Okay, work. We won't be able to do linear motion next time, linear momentum next time. Let me adjust the schedule here. Yeah, we'll have to continue with 5 UCM here. Work like that. As we go along, I will be updating this schedule. Okay. Notes. Going back to chapter 4, we will do some examples of apparent weight. A very important type apparent weight. A very important type of phenomenon. Okay. Example. Example of apparent weight using using Newton's law of motion.
Professor,
Where-
is
yeah.
unicircular motions going to be on the exam?
Which one?
Unicircular motion? UCM?
I'm still deciding. I'm still deciding. It's gonna depend how much we cover.
Okay.
Let's see what I have here. Yeah, so far I I have put only chapter 4 there. I didn't put chapter 5 yet. If you finish chapter 5, I will put it. Next time I will put it here, okay? So just be prepared. But I'm suspecting there's too much material for the second exam.
Yes, it is too much.
Suspecting there's too much material. Most likely I will leave chapter 5 out of this exam. Okay, so he go. Going back to chapter 4, we'll do some examples of apparent weight using Newton's law of motion, a very important type of phenomenon. We will also do examples of apparent weight using circular motion as well, okay? So consider an individual. I'm going to walk you through step by step different types of examples of apparent motion. Okay, consider an individual standing inside, right? Inside an elevator at rest. Inside an elevator that is at rest. The test subject, I call him test subject. Consider a test subject. Okay, inside an elevator. The test subject is at the top of a scale. Okay? Find the normal force that the consider test subject of mass m inside an elevator at rest. At rest means b equal to 0. The test subject is at the top of a scale. Find the normal force that the scale exerts on the test subject. By the way, very important. Very important. Find the normal force, which, by the way, coincides with the reading in the scale. Very important, okay? If you are taking your weight, your mass on the top of a scale, whatever the scale registered there, whatever the scale shows that to you, in reality, is not your weight. It is something else. It is the normal force that the scale is exerting on you. It just happens that under certain circumstances, the normal force coincides with your weight, okay? By the way, which, by the way, coincides with the reading of the scale. Reading of the scale, okay? So solution, okay, the solution, what you have to do, you have to come up with the free body diagram here. Here you go, the test, my test subject on the scale. Let's see, here's the weight of my test subject. Let's see if I can get it. Okay, let me see if I can do. I would love to have everything centered here, right? Yeah, centered, cool. And now I gotta do the same for the next slide. The other one was not centered. Huh. Right here, yeah. Okay, and I have to change the letter here, that's M. Okay, so we're doing a free body diagram of the forces applied to the individual. The weight is always there. And something else is going to be there. It's going to be the normal force as well. And now I'm just changing the position of the weight so you can see those forces more easily, right? Here you go. Now I can remove. I can remove the previous force that you have here. Get used to do those drawings. Hey, look, it's so simple. So, and yet they're so useful. Don't be, don't underestimate the power of those drawings, okay? Of those illustrations, even though they look so deceptively simple. Okay, the head of my test subject is a little bit offset. See here? It's still a little bit offset. Hopefully I got it now. Yeah, I got it. Okay. Identify the forces. Solution. Identify the forces. Normal. Well, the first one that you identify is the weight that's always there, and normal. Right? Apply Newton's law of motion. Since the elevator is at rest, the net force must be 0, right? So, oops. That's what I want. I want to copy it. Here we go. Yeah, we go. Net force. I gotta put also my vector. Oops. Oh, what's going on here? Yeah, sometimes. Okay, now we got it. Net force is equal to the weight plus the normal. And since the elevator is at rest, the net force must be equal to 0. I want to find the normal. I know what the weight is because we have the mass of the test subject, right? And the weight can be written as being the mass of the individual times the acceleration of gravity. That weight plus the normal must be equal to 0, and the normal must be equal to minus mg. Like that. Okay, and one more thing that I'm missing here is the y-axis. Let me put my y-axis here. This is the case of one-dimensional problem. Okay, here you go. I have chosen my y-axis to be upwards. Few grid line guides. No, one of grid lines. Here you go. Yeah. Why? Well, but we also know that the acceleration of gravity in this case is g in the minus direction of the y-axis, right? And just by this simple mathematical procedure, we find that the normal must be upwards. And by the way, note that in this specific case, the normal coincides with your weight. That's exactly what your scale measures. And then we're going to go to the next example. Next level of difficulty for this type of problem. Okay, and let's see. Now, oops. Don't want the grid lines here anymore. Now, the elevator is no longer at rest, but it's moving with a constant velocity. Let's say it's moving upwards. Moving upwards. I'll not even put it at greater than 0, because already saying that's upwards, right? Repeat that. Okay, here you go. Consider a test subject inside an elevator that is moving with constant, that's moving upwards with constant velocity. Of the scale, right? No, of the. Find the normal force the scale exerts on the test subject, which, by the way, coincides with the reading of the scale. Solution? Okay, identify the forces just like before. Apply Newton's law of motion. Since the elevator is moving with constant velocity, it doesn't matter is this upwards or downwards. The net force must be 0 as well, right? That's Newton's second law. And look what we get, we still get the same result. Whether the elevator is at rest or the elevator is moving with constant velocity, the reading in the scale is going to be the same. Things start to change. Things start to change when the elevator is accelerated. Let's see here. Yeah. First, I'm going to put the elevator with a constant acceleration upwards. And then I'm going to put the elevator with a constant acceleration downwards. Okay. Let's see how it changes mathematically. Like I said, it's the concept of apparent weight. Apparent weight means the weight that your scale measures. The weight that your scale measures. Okay, mass elevator is moving with a constant upward acceleration. The test subject is at the top. Find the normal force that the scale exerts on the test subject, which, by the way, coincides with the reading of the scale. Identify the forces, weighted normal. Now we have an additional step. Consider whether the elevator is accelerated or not. And the answer is yes. And now, because the elevator is accelerated, apply Newton's second law of motion, right? Because of the acceleration, you must apply Newton's second law of motion. Because of the acceleration, you must apply Newton's second law of motion. Or now we're going to have mass times acceleration, like that. Okay. Don't forget the acceleration is upwards. And we must have another term right in here.
Professor, can I see
Yeah.
the example 2 again?
This one here?
Yes. Thank you. Yeah, I copied and paste. Thank you.
Okay, so just so far summary, right? So you don't get lost. The summary, you know, v equal to 0, v equal to 0, 1, 2, 3, v equal to constant different of 0, a upwards, constant upwards, equal constant upwards, a equal constant downwards. Those are the downwards less than g, and then we're going to do another one. 1, 2, 3, 4, 5 different types. Downwards greater than g. Greater than g, like that. Okay, that's we did this one. We did this one. We're doing this one here. I'm going to. Right, and now don't forget that the acceleration is upwards. Right? Because the acceleration is upwards, it must be in the positive direction of the y-axis. And look what we get. We get something that sums with the original weight. The scale is going to record a weight that's higher than your own value. Okay, it's like that. Which, you know, I'm going to conclude here. Magnitude of the normal is greater than mg. Okay, you feel heavier. You actually feel heavier, okay? They call it apparent, but it's not apparent. You feel that you are heavier. There's no elevator that behaves like that because, you know, otherwise everybody's gonna throw up inside the elevator, okay? What actually happens is that the elevators, whenever they start moving, they have a very small acceleration at the very beginning, a very small acceleration. That's why we usually feel that pressure on our feet whenever the elevator is moving upwards. Start to move upwards. Once it reaches its final speed, then the elevator moves with constant velocity and you feel your normal weight, okay? So numeric example, right? I'm gonna give you a numeric example. Suppose that we have this crazy elevator in which the acceleration of the elevator is going to be 5 meters per second square. And what means 5 meters per second square? 5 meters per second square is usually represented by half of a g, right? G is 10 meters per second square, half meter per second square. 5 meters per second square is half of a g, numeric value. If we go ahead and plug in this type of solution, what you're going to get, you're going to have 1.5 G's, 1.5 mg, right? You're going to feel 50% heavier. And you do feel 50% or heavier. Don't fool yourself. I have been subjected to something like that. I have experienced something like that. You must have experience too, especially in roller coasters and in those drop towers that they have at the theme park, right? And so, next example, 11 50 right now. Have 10 more minutes to go. Now, consider the subject of mass m inside an elevator that move with a constant downwards acceleration. Test subject at the top of a scale. Find the normal force that the scale exerts on the test subject, which, by the way, coincides with the reading of the scale. Okay. So here you go. Now what we have here, I don't need that. Okay, I don't need that anymore. Interesting. Okay, and now I will go for this one here. But now the acceleration is going to be downwards. Okay. And I don't need that anymore. Example 4, right? Identify the forces, weighted normal. Consider whether the elevator is accelerated or not. Yes, it is accelerated because the acceleration, you must apply Newton's second law of motion, right? But now the acceleration is going to be on the other direction. It's going to be on the negative direction. You go. The y here, right, would be in the negative direction. And look what we end up getting. We end up getting something slightly different. We're going to end up getting something like that. Here you go. I'm going to change. I'm going to commute those two terms. Instead of g plus a, you're going to get g minus a. G minus a. And in this case, and assuming, assume downwards acceleration. One more condition here, a less than g, okay? One more condition here, less than g. Because a is less than g, now your normal is going to be in less than mg. Greater than 0, right? And less than mg. You're going to feel lighter, yeah? And that really happens. Okay, so let's see. This indicator here is going to be a little bit this way here. This other indicator is going to be a little bit on the heavy side. This other indicator is going to be in the normal direction, right? In the correct weight. And note one very important thing. Numeric value, let's say 5 meters per second squared downwards. What's going to be your normal? Your normal is going to be half your weight. You're going to feel half. You're going to feel lighter. Just as though that you're on the surface of the moon. You'll be able to jump higher because the perceived acceleration of gravity is going to be less. Yeah.
But I have a question. Why? Okay, let's say if you throw a baseball in moon, why it goes lower than the Earth? Like, I think why is that? I don't get that problem.
Well, let's see. Let me see. The baseball, if you throw a baseball on the moon, the ball is going to move further away. It's going to fly high.
Further away, but it's lower. Why is that?
What do you mean lower? What do you mean lower?
That's what I didn't get. I saw this like question from, problem from textbook. It was like telling me that if you throw baseball in moon, it will go further
Yeah.
But at the same time, it will go lower or something like that.
Well, you gotta show me which problem is that in the book, right? Do we know the problem that you're referring to?
Oh, let me find it. But go ahead.
Okay, so in the case of the moon, okay, in the case of the moon, right? I'm gonna spell that out here. If you throw, right, a baseball with the same velocity, right? Same velocity and angle as you do on Earth, right? The ball will fly further and higher, the projectile, okay? Why is that? Why is that? That's because the acceleration, the acceleration of the acceleration of gravity on the moon's surface is lower than the acceleration on Earth. Okay, that's why. That's why, because the acceleration is lower, the ball is gonna fly further and higher. Okay, with the same velocity and same angle of same projectile angle. Okay, and you get a similar result when you're inside this elevator that is accelerating downwards. An elevator that accelerates downwards make you feel lighter. An elevator that accelerates downwards gives you the impression that the acceleration of gravity decreased. Okay, until the point. Now, what happens when the acceleration becomes 10 meters per second square, right? What happens when the acceleration on the elevator is going down? What if the elevator is accelerated downwards at 10 meters per second square, right? Oh, you just apply the equation that we got here. Okay, look what we get. You get, let's see, I'm gonna do like that. We're almost running out of time here. And hopefully I'll be able to do, here you go. If the acceleration of gravity is exactly g downwards, what's gonna happen? You're gonna get the sensation of weightless. Okay, you're gonna float inside the elevator. That's something that really happens and has been dramatized in many movies out there. Okay, it's the case, for instance, that movie from Leonardo DiCaprio that I watched recently. What's the name of that movie? Gosh, I'll remember. The guy goes inside the mind of the others. They interfere with their dreams, right? And anybody remember the name of this movie? Inception. In the movie Inception, right? In the movie Inception of Leonardo DiCaprio, they dramatize this weightless sensation inside the van while they are inside someone else's dream, right? Someone else's dream. It was very realistic. They did a pretty good job. Someone else's dreams, right? They did a very good job. Did a very good job dramatizing the situation. Very realistic. And that's exactly what you get when the elevator is going downwards, accelerating downwards when you cut the cable of the elevator, right? You float there inside the elevator. But then something else interesting happens if you accelerate the elevator even more. Not just cut the cable, but you install some rocket engines here at the top of the elevator to make the elevator accelerate, let's say, at twice the acceleration of gravity, 20 meters per second square. what happens in this case? Okay, upwards become downwards. The scale starts recording a negative weight, and you can even walk upside down like this guy is. Take a look at the hair of the other one. Okay, and I'm going to spell that out here. We're almost done, right? Yeah, not this one right here. If in this case, also in this case, if A is greater than G, right? Then you have negative G, and you can walk upside down just like a fly, upside down just like a fly. Okay, and that's exactly the sensation that you get under those circumstances. Okay, so we are done here. Let me take a look at Camden baseball. The pitcher's mound is raised to compensate for the fact that the ball falls downward. What's mound? It travels from the pitch to okay, on the moon. Would the pitcher's mound? What's mound? Mound is the glove.
Mound is like a ground, I think. Yeah, like. But I think I misunderstood. I thought it was talking about the ball, but it's actually talking about the mound. So, yeah.
And what's the mound? I do not know what the mound is. Let's see. Mound. Is anything related to baseball?
Yeah.
Let's see. Mound.
It's like where where the pitcher stands and throw the ball.
Or the pitcher send. Well, mound that I see here is something like that. Let's see.
Yeah,
mound.
it's like that, but it's like much. Lower.
Much lower. Much lower.
Yeah.
Okay.
Yeah.
In baseball, the pitcher's mound is raised to compensate for the fact that the ball falls downward as it travels from the pitcher towards the batter. If baseball were played on the moon, would the pitcher's mound have to be higher? I see, lower than. Okay. And then it has to be lower, right? Let's see. If the baseball were played on the mound is raised to compensate for the fact that the ball falls down. Yeah, that's right. That's right. So yeah, the mound would have to be lower on the moon surface. Okay, so the mound is the place where the pitcher is, right? So they have a little mound there, a little hill there for the guy to throw the ball, right? To compensate for the fact that the ball is falling, so the ball is gonna hit exactly, roughly on the same height that it was thrown. That's way it is. Okay.
Yeah.
Any more questions? Okay, so we are done here, and we'll meet again on Wednesday. On Wednesday, I'm planning to have your lab reports corrected. Okay. I see you on Wednesday again. I'll be here for the office hours.
Thank you, Professor.
Welcome.
And she